Hey everyone, and welcome to this explainer. Whether you're a computer science student getting ready for the job market or a working data engineering pro trying to untangle some messy pipelines, you are absolutely in the right place. Today, we're tackling a high-stakes scenario that really separates the novices from the experts. We're going to master one of the most notorious challenges in big data. Picture this. You're sitting in the hot seat during a top-tier data engineering interview, and the interviewer slides this question across the table. Your output contains 250,000 tiny Parquet files. How would you fix this? I mean, it sounds super simple, right? But watch out, because this question is actually a massive trap. It's specifically designed to test your core knowledge of Spark execution, partitioning, under-the-hood shuffles, and how cloud storage systems actually work in the real world. Okay, let's dive right into this. Here's our roadmap for today. First, we'll define the tiny files problem and exactly why these files hurt your performance. Then, we'll find the root causes, cover 7 concrete Spark optimizations, calculate exact partition numbers, and finally, construct the absolute perfect interview answer to seal the deal. All right, let's kick things off with Section 1, the tiny files problem. So to actually fix this, you really need to understand the mechanics under the hood. Spark divides your data into partitions, right? And here's the golden rule you need to remember. Every single partition writes exactly one output file. If Spark has 250,000 partitions sitting in memory, well, it's going to dump 250,000 tiny Parquet files onto your storage disk. And that is the total disaster you see on the left. Contrast that with the optimal state on the right, which shows a clean 1,000 partitions translating into 1,000 perfectly sized files. Which brings us to Section 2, why tiny files hurt. When this problem hits your pipeline, it is literally a slow, expensive death by 1,000 cuts for your data lake. You're looking at 4 main casualties here: metadata overhead, driver overload, steep object storage penalties, and a massive explosion of unnecessary Spark tasks. Let's break these down so you know exactly what's failing behind the scenes. First up, metadata overhead. Imagine having to read a novel, but instead of a normal bound book, every single sentence is sealed in its own individual envelope. Exhausting, right? That's exactly what reading 250,000 1-megabyte files is like. Spark has to open every single file, read the footer metadata, and schedule a task for each one. Most of your processing time is completely wasted just opening files, rather than, actually reading the data. Contrast that with reading 250 1-gigabyte files. That's lightning fast, because the overhead is basically nothing. Second is driver overload. In Spark, the driver node is the brain of your whole operation. It has to keep the metadata for every single file active in its memory. So if you throw 250,000 files at it, that driver's memory fills up incredibly fast. This massively increases the time it takes to plan the execution, and in worst-case scenarios, it'll just flat out crash your driver. Third, and this one really hurts, let's talk about your wallet. Cloud object storage systems like Google Cloud Storage, Amazon S3, or Azure Data Lake, they charge you based on API requests. Every single file means another read or write request. Thousands of tiny files mean thousands of expensive and slow requests, totally penalizing both your processing speed and your cloud budget. And finally, the fourth issue. Because each input file generally creates one task, you end up with 250,000 tasks. Task scheduling overhead just completely dominates your execution time. Moving on to Section 3, finding the root causes. To actually fix the pipeline, we need to figure out what Spark mechanics are causing this mess in the first place. Usually, the culprit is one of these 4 things. Someone might have called the repartition function with a huge, totally unnecessary number. Or they used partition by on a high cardinality column, meaning a column with way too many unique values. It could also just be a streaming job that's writing tiny microbatches every few seconds. Finally, Spark's auto-scaling feature, dynamic allocation, might just be leaving too many partitions active. All right, time for the good stuff. Section 4, 7 Spark optimization solutions. So there isn't just one universal fix here, but we do have 7 practical heroes to help you take back control of your cluster. Now, what's really interesting about this is the critical difference between Coalesce and Repartition. This is solution 1 and 2. And honestly, it's a huge favorite for interviewers. If you just need to reduce output files, use Coalesce. Why? Because it merges partitions and avoids a full data shuffle, which saves a ton of processing time. However, if you've got a massive data skew, like one partition is 500 gigabytes and the rest are tiny, or you actually need to increase partitions, you absolutely must use Repartition. That one performs a shuffle to redistribute the data evenly. Solution 3 is controlling your partition by statements. Writing data partitioned by a high cardinality column, like user ID for a system with 5 million users, creates absolute directory chaos. You get millions of directories with tiny files inside. Instead, you want to choose a low to moderate cardinality column, like date or country. This keeps your whole file hierarchy clean and manageable. Solutions 4, 5, and 6 are all about your configurations and operations. First, you've got to tune your shuffle partitions. The default is 200, but people often set it to like 5,000 without any good reason. Adjust it to actually fit your data size. Next, enable adaptive query execution, or AQA. AQA is brilliant because it can automatically merge small shuffle partitions into larger ones before writing. And hey, what if the tiny files already exist on your storage? Solution 6 is to just run a periodic compaction job. Read the 250,000 files in, use Coalesce to bring it down to maybe 500, and overwrite the directory. It's a really quick operational fix. And solution 7 is to always keep the golden rule of per K file sizing in mind. Your target file size should be roughly 128 megabytes to 512 megabytes. If files are too small, well, as we've learned, metadata overhead destroys performance. But if they're extremely large, say several gigabytes each, you actually reduce Spark's ability to read them in parallel. So 128 to 512 is absolutely the sweet spot. Okay, let's get into section 5, calculating exact partition numbers. You know, it's one thing to say you'll just reduce partitions, but it's a whole other flex to mathematically prove to an interviewer that you know exactly what number to use. Here is a super practical heuristic. The formula is actually really simple. Total data size divided by your target file size. Let's say you have a 1 terabyte dataset, which is 1,024 gigabytes. You choose a target file size of 256 megabytes, or 0.25 gigabytes. Divide 1,024 by 0.25, and you get exactly 4,096 partitions. So in your code, you write df.coalesce 4,096. In the real world, sure, you might adjust slightly for data skew or compression, but laying out this math shows you absolutely know what you're doing. Finally, section 6, the perfect interview answer.
All right, we've covered the mechanics, the pain points, and the math. Now let's bring it all together into a single, highly polished elevator pitch. The crucial thing here is delivering this with total confidence. You look at the interviewer and say, tiny Parquet files are usually caused by too many output partitions or high cardinality partitioning. I would first identify why the files are small, then reduce the output partitions using Coalesce if I just need fewer files, or repartition if I need to rebalance skewed data. Moving forward, I'd avoid high cardinality columns, tune my shuffle partitions, enable adaptive query execution, and target roughly 128 to 512 megabytes per file. And if the files already exist, I'd trigger a compaction job. Boom, you just aced the technical screen.
And that is a wrap on our breakdown. You now have the tools, the math, and the vocabulary to solve one of the most frustrating problems in data engineering. So I'll leave you with this. Will you let tiny files crash your next pipeline, or will you step up and take control of your partitions? Thanks so much for tuning into this explainer. Keep learning, keep optimizing, and I'll see you next time.